So what if I told you that the silent pull of a compass and the very power lighting up your screen are actually the same exact thing? Well, they are. They're two sides of one of the most fundamental forces in the universe, electromagnetism. Today, we're going to pull back the curtain on how it all works, the rules that run the show, and the amazing machines that it powers. Let's get right into it.
You know, for the longest time, everyone, and I mean everyone, thought electricity and magnetism were totally unrelated, right? You had the crazy, raw energy of a lightning bolt over here, and the quiet, weirdly magical pull of a magnet over there. They were just two separate chapters in the big book of physics. Nobody saw the connection.
But then, in 1820, everything changed. A scientist, Hans Christian Oersted, was in the middle of a lecture, and he noticed something odd. Every time he turned on an electric current, the needle on a compass sitting nearby would just jump. It was a complete accident, but that little twitch was the first real proof that these two forces weren't just strangers. They were partners in crime.
And this discovery blew the doors wide open. See, it's not just that one affects the other. It's a two-way street. It's perfectly symmetrical. Electricity can create a magnetic field, and as we're about to find out, a magnetic field can create electricity. And that beautiful relationship, well, it's the key to basically our entire modern world.
All right, so let's start with Oersted's side of the street. How in the world does an electric current, which is really just a bunch of charges flowing through a wire, manage to create a magnetic field literally out of thin air? Well, in its most basic form, it's actually pretty simple. You pass a current through a straight wire and poof, a magnetic field just appears around it. And it's not some messy, random cloud of energy. Nope, it's a super organized pattern of perfect concentric circles with the wire running right down the middle. Okay, so which way are those circles spinning? For that, we've got a brilliant little trick called Maxwell's right-hand thumb rule. Seriously, you can do this right now. Take your right hand. Imagine you're grabbing the wire and point your thumb in the same direction as the current. The way your fingers naturally wrap around it, that's the exact direction of the magnetic field. Easy, right? Now here's where it starts to get really powerful. What happens if we bend that straight wire into a circle? All those little circular field lines start to team up in the middle, creating a much stronger, much more focused field. Right at the very center, the field lines get packed so tightly they become almost perfectly straight and parallel. And this is the first step to building a real magnet. So, if one loop is good, what about, say, 100 loops? Well, that's what a solenoid is. It's just a long coil of wire with tons of turns. And when you send a current through it, something amazing happens. All those individual magnetic fields merge into one powerful, super uniform field inside the coil. And get this, it behaves exactly like a regular old bar magnet, with a true north and a true south pole. So how can you tell which end is which? Easy. Use the clock rule. Just look at the face of the coil. If the current is flowing in a direction that looks like the hands of a clock moving backward, anti-clockwise, that's your north pole. And if it's flowing clockwise, well, that's your south pole. It's a super simple visual check that works every time.
And this ability to be a magnet only when we want it to be is what we call an electromagnet. See, unlike a permanent magnet you'd stick on your fridge, which is made of steel, an electromagnet is temporary. We usually build them by wrapping a coil around a soft iron core. And why soft iron? Because, and this is the whole point, it becomes a strong magnet when the current's on, but it loses almost all of its magnetism the instant you switch the current off. It's that on-off switch that makes it so incredibly useful.
All right, we've gone down one lane of our two-way street. We've seen how current makes a magnet. So now, let's switch gears and head back the other way, thanks to a mind-blowing discovery by the legendary Michael Faraday. How can a magnet create an electric current?
This phenomenon is called electromagnetic induction. Now there's one word here that is more important than all the others: changing. If you just let a magnet sit next to a coil of wire, absolutely nothing happens, zero. But the second you start to move that magnet or change the field somehow, a voltage, what we call an electromotive force, suddenly appears in the wire. You are literally creating electricity from nothing but motion.
Faraday boiled all this down into two fundamental laws. First, you only get a voltage when the magnetic flux, you could just think of that as the number of magnetic field lines passing through your coil, is actually changing. Second, the amount of voltage you get depends on how fast you make that change. The quicker and more dramatically you move the magnet, the bigger the voltage you generate. It's all about speed.
So which way does this brand new current flow? This is where Lenz's law comes in, and honestly, it's kind of funny. The induced current is, well, it's a bit of a rebel. It always flows in a direction that creates its own magnetic field to fight against the change that created it in the first place. So if you try to push a north pole into a coil, the coil will instantly create its own north pole to push you away. Nature's not just being difficult here, this is the law of conservation of energy in action. You can't get free energy.
Okay, I know. We've got forces, fields, and currents, all interacting and pointing in different directions. It can get confusing, fast. So to keep everything straight, physicists came up with a set of hand rules. This is where a lot of people get tripped up, so let's clear it up once and for all.
Let's break these down, because they each have a very specific job. Maxwell's right-hand rule, that's just for finding the direction of the magnetic field created by a current. Simple. Fleming's left-hand rule is for motors. It tells you which way something will move when you put current into it. And Fleming's right-hand rule, that's for generators. It tells you the direction of the current you get out when you move a wire. Easiest way to remember? Left hand drives the motor, right hand generates the power.
Now these rules aren't just for exams. They are the actual design principles behind some of the most important machines ever invented. This is where all that theory comes to life.
A DC motor is basically Fleming's left-hand rule in action. You pump electricity into a coil that's sitting inside a magnetic field. That combination creates a force, which gives the coil a kick and makes it spin. But here's the genius part. To keep it spinning, it has a little device called a split-ring commutator. Its only job is to flip the direction of the current every half turn. This keeps the kick always pushing the coil in the same rotational direction.
Now, a generator is just the beautiful mirror image of a motor. A motor turns electricity into motion. A generator, following Fleming's right-hand rule, turns motion back into electricity. And look at the key difference in their design. Instead of that split ring that flips the current, an AC generator uses two full, unbroken slip rings. These just let the current flow out exactly as it's being made, alternating back and forth, which is what gives us the AC power in our homes.
And there is one last, absolutely essential device we need to talk about, the transformer. It uses this cool principle called mutual induction. Basically, the changing magnetic field from one coil can create a current in a second coil right next to it without them even touching. And we use this to change AC voltage levels.
And the magic trick is just the number of wire turns in each coil. If your second coil has more turns than the first, it's a step-up transformer, and the voltage goes up. If it has fewer turns, it's a step down, and the voltage goes down. This simple idea is the hero of our entire power grid. It lets us step up voltage to send power across the country efficiently, and then step down that voltage so we can safely charge our phones.
So, let's just boil it all down. If you remember nothing else, remember this. Oersted showed us that current makes magnetism. Faraday showed us that changing magnetism makes current. For the hand rules, it's simple. Left hand for motors, right hand for generators. And if you need a magnet you can turn on and off, soft iron is your best friend.
Okay, quick check to see if you were listening. A transformer has 100 turns in the primary coil and 500 in the secondary. What is it? That's right, it's a step-up transformer. Why? Because the number of turns in the secondary coil is way bigger than the primary, which means the output voltage is going to be 5 times higher. And all of this leads to one final huge question. Realizing that electricity and magnetism were just two faces of the same force completely revolutionized physics. So it really makes you wonder, doesn't it? What are the forces that we think of as totally separate today, like gravity or the forces inside an atom, are just waiting for someone to have their own Oersted moment and show us that they're all secretly connected too?